So, like I said, it's an introduction to exoskeleton. You can see some example and application and future trends for your exoskeleton project. First, we will see what an exoskeleton, the example of inspiration and reality, applications in space and Earth, and future trends. And first, what is an exoskeleton? When you take the definition in Collins Dictionary, it's a protective or supporting structure covering the outside of a body of many animals, such as the thing cuttle arthropod, or you will see better after with crabs. They have many exoskeleton. The same with the definition for us for your project. It's more an exoskeleton or mechatronic system worn by a person in such a way that the physical interface permit a direct transfer of mechanical power and exchange of information. And first, I will want to show you the inspiration, because it's the inspiration that help a lot the engineer and biologist to understand how to do an exoskeleton. So when first I will begin with fiction. We have many anime like Gundam or other animation like Code Geass. Also, they have all exoskeleton. Okay, it's not the exoskeleton, you know, but it's really really an inspiration for the scientists. But you have also in a movie like Animatrix, the APU, the I don't know if you see that, but it's also an exoskeleton. Or Iron Man. Iron Man have many inspiration for NASA or other exoskeleton that exist now. The other things you can inspire is crustacean. Like I said, many crustacean have an exoskeleton. In biology, we study this material structure because it's really strong and really impressive. So when you see the crustacean, they have a honeycomb topology. Its structure really strong. So you can maybe see it, think about it for your structure. But also the insect as a model, like cockroach. We try to understand the structure and the exceptional locomotor capacity, because they have a big structure, really strong, but we don't understand how they can have a speed locomotion and really impressive to move fast with this kind of exoskeleton. So now what we have like exoskeleton, they have many examples of exoskeleton now. It's just some. I will explain you like more the biology way of the exoskeleton, because I'm more in biology. The more used is the EMG. It's used to exoskeleton skeleton interface control for if you can do a movement. If you have a spinal cord injury, you can do a movement. I don't know. It depends the level of your injury. But if you can move your legs, but you can send a signals, you can cap these signals. So Fisher and Arnold here explain this kind of interface control. It's a control system by biological signal. It's the EMG signal. It's a desire of movement. So you will see this kind of system with Dr. Bélanger. And the name of EMG is electromyography signal for muscle contraction. So it's the signal before the activity. Another meal signal, well, you have EMG, but for arm, you can use it also. It's for all the muscle, but I want to show you some example. So it's general signal in the arm to amplify the load carrying capacity. In this case, it's the people can move the arm, but you amplify the load. You can take, I don't know, a mini rice bag, like in I see some things on YouTube. You can see also on some exoskeleton, and you can just amplify the load that someone can take. So the problem is the algorithm of EMG signal. It's difficult to have a good interpretation of this signal because you have many movement and a simple articulation. So it's difficult to know if you want to go in front, if you want to go in back, if you want to have a rotation. And more you have articulation, more it's difficult because you have many freedom degree. So it's really difficult to analyze and algorithm this signal. So the Blex, I think it's the more documented exoskeleton. I put just one of the article. I can send you more. It's activated by the movement of legs. So by the locomotion of the people. So like this is a military section. So the army just go walk and have a locomotion. So the foot and the toes have a movement, but all the transfer of load and it's on the ground. So the distribution sensor help to take a very heavy load, but you have to be able to walk. so it's difficult. We'll see with astronauts, it may be difficult for the astronaut to use this kind. We can use it, but we have to see if they can move and march. So Expose is another exoskeleton, really impressive in Japan. So I put it also in the article. So it's a synchronous of human and robot. So it's for senior people for rehabilitation, decrease load and stabilize, because with people, senior people, it's really difficult to stabilize the walk, and they are really afraid to fall, because if they fall, they can have a fracture. The most important is stabilize, because with the old people, we'll see after, we really need a big balance. And this exoskeleton, the more important, it's the design control, because it's with pressure sensor. So with the contraction of muscle, you have a picture here to understand more. So the people walk or squat or everything, and they give signal for a sensor. So it's a control for this kind of exoskeleton. So the application, for me, it's really a big part, really important, because it's the biologic side, really important to think when you do your exoskeleton. We will see in first space exploration. So osteoporosis, they have a long flight, and if they don't have a human countermeasure really effective, it's sure they have osteoporosis. So really big risk to have a fracture. And we don't have this in Mars. So you have to think about it. If they don't have human countermeasure efficient and the space, you need to have an exoskeleton that take all the structure really stable, and be sure they don't fall, they don't have a problem when they change the exoskeleton to go, I don't know, in the bed or in the space flight. So they have to think about it. Muscle atrophy is the same way. You have a long duration flight, so they have an atrophy in muscular, so they cannot carry a load, or they have a risk of ruptured tendon, and the same also with the injury of muscle. They have some alteration in sensory perception. It's really short a rehabilitation, this alteration, but you have to think about it, because they have an alteration in locomotion function. So if you design your exoskeleton with this locomotor function really like a human on Earth, it's maybe not the same when we go on Mars. So you have to think also at the alteration, but also to the distribution of blood volume. It's the same. It's a really short rehabilitation if you compare with the osteoporosis of muscular atrophy. But if you have a big work day, you have a cardiovascular response maybe really difficult, and they can do this kind of work. Also, the respiratory support, you have to think about if they have a spacesuit with the exoskeleton, or if the exoskeleton is the spacesuit. Because with the respiratory support, you need to know with the respiratory effort, if they need exchange of O2 or CO2 different, they have a pressure more, or depending on the environment, if they have a particle really dangerous. So you need to think about everything about the respiratory support. Senior people, like we see with the other exoskeleton, they have osteoporosis too, so the big risk of fracture, and they really fear about this. They have also sarcopenia. Sarcopenia, it's muscular atrophy, but with aging, it's the difference. So they cannot carry load, and they have sometimes really difficult with balance. The balance is the more important with senior people. It can be neurologic, but it can be sarcopenia, or it can be also just dysfunction. So how you can do this really secure for falling and for fracture, because they have a big fear. The biggest fear of senior people, it's to fall, because some people in this age to fall and have a fracture go at the hospital for an operation and can die during this operation. So it's the biggest fear of these people, and they maybe just do not want to try it because they have fear to fall. Rehabilitation after trauma, in this case we will talk about the car accident. It depends on the trauma. Cranial cerebral trauma, it's a movement coordination very difficult. It's and cerebral, so they cannot coordinate the movement, and they have a fatigue really easily. So you have to think about it. If they don't have coordinated movement and your exoskeleton, you have to give an information really simple of movement, or you have to direct some movement. So you have to think about it. Traumatized by accident like fracture, break tendon, you cannot use some part of the body, cannot carry load. You need to work with the doctor to know what you can do, what you cannot do. It's more difficult in rehabilitation center. Spinal cord injury, we'll talk a little bit more about it. You cannot move some part of your body. Fatigue is the more important thing in rehabilitation, because in the first part of rehabilitation, they cannot more than a few minutes. With time, they can do more, but it's really difficult for the people to begin with the fatigue, because they have to rest. So you need to know how they can rest, if they can sit on a chair or no. So you have to think also about this. And psychological, we don't think about it often, and it's very important in rehabilitation, because the motivation, the denial, sometimes they just don't want to have a rehabilitation, or said, okay, my life is finished, so I cannot continue, and the exoskeleton doesn't work in this time because they just don't use it. So I will talk a little bit more about spinal cord injury. It depends on the level, and it can be complete or partial. In the case of it's complete, so if it's complete, in this case, if I cut here, so I cannot use abdominal muscle, I cannot use leg muscle, I cannot use all this in the bottom. Hopefully now we have more partial level of spinal cord injury. It's good. You can use sometimes some of part below of the injury, but it's really difficult. So you cannot move some part of your body. You have to think about it. The fatigue too. So we can work more than a few minutes in the first. They have risk of osteoporosis in the case of paraplegic. The leg doesn't move, and they have osteoporosis on the tibial or the other bones and leg, because they don't use it. So the exchange is not very easy, and they have a big risk of fracture, because if you go in the bathroom and you have to change that your chair, you can just fall and have a fracture. So it's really important to think about it. Muscular atrophy too. You see, if you don't use it, you lose it. So you cannot move. Difficulty to move a muscle around also, because you say, okay, I cannot move it, so I cannot move it around too, or I don't have I don't want to do some exercise because I'm paraplegic, so I don't need it. It's difficult, and it's psychological thing, the most important in this case, because some people have a big motivation to rehabilitation and want to really move every muscle and can do many things. But if they denial, if they don't have a motivation, it's really difficult to preserve some muscle. Loading work, it's worker for like box and an industry or everything. We don't think often about this, but it's really important. It can be military too, and it's for this reason we have a program in UCAM too about ergonomy and work, to be sure they don't have difficulty to do the work of our injury. It depends on need and function tasks. They have some change sometimes in locomotor pattern, because they said, okay, I can put this box there. It's more easy if I just turn this my abdominal muscle, but I don't use my leg. So sometimes they have some muscle maybe really strong and other no, and it can be difficult in locomotor pattern. So it can be also a risk carrying back technique, have an injury, something like this. Duration of work sometimes is really crazy. You think also about the battery, but more it's human fatigue. So injury, they have so many hours of work. It's sure it can be too difficult to just think about the movement. Task type, like weight, size, freedom of freedom degree, depend the industry. They have a table, they don't have it, or they have to change, have the rotation. The rotation is really bad sometimes because they do that really wrong and have many injuries. So you have to be really careful about this. Walking stress too. So it's like dexterity, risk. Sometimes they take really big risk because the machinery or worker needs to do some risks, so you have to think about it when you do your exoskeleton too, because maybe the exoskeleton would be so big and would be a big risk for the worker. And it's the same of the mask and the suit. They have the mask and the suit with the exoskeleton or without. So it's important to think about it too. And the psychological thing, it's really funny, but the worker culture is the worst. Sometimes they said, "Oh yeah, I don't need a helmet. I'm a big guy, so I don't put it." And it's not a big problem. So they need information. They need really to understand why it's important to have it. And I really talk fast, so I will talk about the application. I will just slow down a little bit. So how it's a hybrid assistive limb. If you see it on the web, it's really interesting. They have many movies about it. It's a robotic. It's the future, so it's exoskeleton robotic. It's inspired by fiction, but when you see this on the YouTube, they talk about it. It's really funny, so you can see it's worked very. It's really good, so you can see that and use it like inspiration. But the more important for biologists is this biologic signal recognition. EMG is good, but the precision, and they have many axes on the arm and everything, so it's difficult to know, do you want to go in front, do you have a rotation, do you want anything, so it's difficult to know what is really the movement you want to do with the exoskeleton. But there exist other signals, like cerebral activity, like Asimo, if you know it, they have some talk, and you can move the robot with your brain. They have cerebral activity, they have spinal cord activity too, but the more difficult is really to focus on this signal. You have they want to set that, so they want to set you go in the front, you have a rotation, you have a flexion. It's difficult to separate this because it's the same signal, but you have to this is for the leg, this is for the arm, this is for the. It's more for this reason. It's difficult to have a good algorithm for the signal. Be careful with the other physiological constraints, so osteoporosis, muscle atrophy, cardiovascular response, and dysfunction. So it's what we see with the other population. So just see what is your population, what is the big constraint and physiology, and we'll be really great with this.